what I intend to do this morning is to revisit the existence and uniqueness theorem that normally we give in any first course in the theory of differential equations, and then show its connection with the what is called the contraction mapping principle. Okay, so in short, I will be proving the theorem using contraction mapping principle. Now let me first pose the problem. So the problem is, we look at this initial value problem, y dash equal to some omega contained in R, where omega is assumed to be open connected. In R. Now, in this problem, x is taken as the independent variable, y is taken as the dependent variable. Now, we are given a point x naught, y naught belonging to omega, and we have the initial data yx naught equal to y naught. Now, this is the initial value problem that we have. We assume f is continuous, real valued. The problem is, does there exist a solution for this problem? I will clamp more conditions on f whenever it is required, but for the time being, we just assume it is a continuous function on omega. So the picture is something like this. This is your omega. It may be bounded or unbounded, it doesn't matter. Now x naught, y naught is a point on that. So some coordinate system is there. Now x naught, y naught is a point on that. Now what you have is, this is the x-axis, this is the y-axis. What you are asking for is this: the function f is defined everywhere in omega. It is assumed to be a continuous real valued function, and x naught, y naught is a point in omega. Now what we are asking for is, does there exist a solution for the equation y derivative equal to f of xy, yx naught equal to y naught? I don't have time to go into the geometric interpretation of this and so on. Now, what one does usually to attack this problem is the following. We convert this problem to an integral equation. This is Picard's method. So what one does is, if y equal to yx is a solution of this, then you see that you have y derivative of x equal to f of xy for some x belonging to some interval ab. I mean, that's the, I am just converting this. Now you integrate a to x, y dash x, y dash t dt. This will give you integral f t yt dt. Something like this. And this part you can integrate and you get yx minus ya equal to integral a to x f t. So what one gets is the following. Now I can write this, therefore you have now an associated integral equation given by y equal to some ya plus integral a to x f t y. So this is some constant, say something like y naught. Okay. Since we are interested in the neighborhood of the point x naught y naught, we take this point a to be x naught. So this is what it is. So this is the integral equation that you have to solve for y, and one can prove the equivalence of the two. That is, if you have a solution of this integral equation, then it gives a solution of the initial value problem. Conversely, any solution of the initial value problem is a solution of the integral equation. Therefore, it's very clear. What it says is that this integral equation is completely equivalent to the initial value problem that you have. Okay? Therefore, if you are interested in finding out whether there exists a solution for the initial value problem, then it is enough to work on this integral equation and show that it has a unique solution. Okay? This is exactly what is mentioned in say in the book How to Solve It by Polya, in which it says if you cannot solve a problem, given problem, what you do is you try to convert it into another problem which is more amenable, and this is what is done. Now what we hope is that we can do something better on this than this. Okay, I am pretty took on this because there are a lot of things that can be said at this stage. Now if you look at this, what is the solution? The solution y is, you see, look at this equation. This equation is an equivalent equation to the initial value problem. We have not solved it because you see that y is involved here, y is also involved inside the integral and inside f. Okay, therefore we have only converted the problem and not solved it. So what we want to do is to find a y on some interval. So we want to have a y on some interval x naught minus h to x naught plus h such that it satisfies let me call this 1. Okay. 2. It satisfies 2. This is what we are after. So we want to find an h precisely, so that you get a local solution of the integral equation, which in turn becomes a local solution of the initial value problem. Now let us have a hard look at this. What does it say? Now let me write y of x to be equal to sum a of yx, where a of yx therefore we have now an operator. A maps a certain class of functions. Let me call this some CAB or something like that. Some continuous function on the interval, some interval I. Let me write that. I will be more specific on this interval. And what happens if you start with a continuous function here and f is continuous? Therefore, you see that when you integrate, this is continuous, and you will get it's even differentiable. And then integrate this and then add y naught to it, so you get a new function. Okay, so what you have is a new function, right? Therefore, A maps a function from Ci into I with some conditions. with some conditions. Let us assume that on F. That's right, exactly. So you have now Ci, and I'll just, so this is a set. Let me call this X equal to Ci. I make all these things more precisely. So what you are having is A is a map from this class into itself. Okay. So what is your problem? Your problem is find a y such that y is equal to ay, or in other words, you are seeking a fixed point now. Does it leave? Does A leave one point fixed under this map? And that element is going to be a solution of this problem. So we have an abstract problem. What is that? Now let me just pose this abstract problem. The abstract problem is this. X is a complete metric space. And A is a map from X. Now the question that you are asking is, does, under what conditions A has a unique fixed point? That means a set X such that X is equal to Ax. Whether this has a solution or not. X is equal to X has a solution or not. Does it have a unique solution? Now this is the problem that you have. Okay. Let us see how this is. Now you see, we have come from a very concrete problem, started with an initial value problem, converted into an equivalent integral equation. Then we discovered that it leads to a what is called a fixed point problem on the interval on the class of functions Ci. Okay, so we look at the more abstract problem, and what the Bowser's fixed point theorem says is the following. See, we have assumed X is complete because that is required to talk about the convergent existence of the limit of a Cauchy sequence, etc. In the process, I don't have time to go through the proof or anything. But what you have is this. Now we have the following assumption is necessary. Assume A is a contraction. What does it mean? It means if D is the distance function giving the metric, then what we need is that D of Ax, Ay is strictly less than or equal to alpha times D of xy, where 0 less than alpha less than 1. Which means geometrically, see, Ax and Ay are the image points under A of x and y respectively. So what you need to say is that A maps x and y to two other points. Now the distance between x and y, you compare the distance between x and y and compare the distance between Ax and Ay. What you say is that Ax and Ay has come closer than x and y. Now this is what you mean by a contraction. So this is the condition that we do have. Now the theorem says that you can prove this abstract theorem. This abstract theorem says that if X is a complete metric space, under what conditions A has a unique fixed point. Now if you assume A is a contraction, then A has a unique fixed point. That means there exists exactly one X with the property that Ax equal to X. Therefore, the additional condition that you have to put in is, we are assuming A is a continuous map. A is a continuous map from X to X, and it is a contraction, of course, that will follow from here, but it can be obtained from here. Okay, in that case, you see that this is a unique solution. Therefore, what we do is now we work on this problem and convert it into the language of the fixed point theorem. Now, incidentally, let me just spend a moment on the contraction mapping principle. I'll just give a very interesting example. The interesting example is, all of you would have seen what is called the ring that you use while stitching to keep the cloth stretched. Okay, so it's something like this. I just draw the picture of that. Okay, so let me just take off all this. See, what you have is, there is a sort of ring that you have with a sort of thing here and so on. And what you do is you keep the cloth here and stretch it, and then put another ring and then close it, so that you can do the stitching without any problem. Now what one does is, what experiment you do is the following. You take a rubber sheet, a stretchable rubber sheet, stretch it in all directions and clamp it inside this ring, as you do with the cloth. Then what one does is, you just first initially you clamp it without stretching, and then mark the boundary. So you get something like this. Now what you do is you stretch in all directions and then clamp, and then mark the boundary. That is, you put a pen and just mark the boundary. And then what you do is you just release it. What will happen? It will contract. So the points inside this whole ring would have contracted into this. Okay? Right? What you do is you stretch this, mark it, and then release it, and then that stretched portions will come inside. This is what you obtain. Okay? So what will happen? So what is happening is that the points here moves into this one. Okay? What more is there? Because of our stretching, if you take 2 points here, say anywhere here, maybe even inside, what happens is, their images that you have is 2 other points, and the distance between them is smaller because we did the stretching and then releasing. Okay? Therefore what you have a contraction. So all the points between, the distance between them have come closer once you have contraction. Okay? And then what the theorem says is that there is exactly one point in this which has not moved from its position, or there is one and only one point which has not moved from this position. Now this is a way of explaining it. Of course, the most famous article that appeared sometime in the late 60s in American Scientific American was talking about the coffee stirring problem, and I think we can. I don't have time to spend on that, but what it said is that you take the coffee cup, stir it, and then what happens is all the points are redistributed. Now, what it says is that if the points have come closer somehow, in that case you have a fixed point in that, a unique fixed point. Now this is the fixed point, but I think I would prefer a analogy of this kind than coffee stirring. But the important thing is that this problem was much discussed at that stage because it was found out as a very strong technique to handle many of these existence and uniqueness theorem. Even now in partial differential equations, you can see that this particular result is very frequently used to talk about the existence of solutions of the differential equations. Now that's a very interesting part. I don't have, if I had time, I could spend a lot more on that and even go to this. I mean, it would be nice to look at the proof of this theorem. The method is very simple. What is done usually in Picard's approximation, to start with an initial point, map it. So you start with some x0, map it, and then you get x1, then you map it, you get x2, and so on. So you get a sequence xn with the property that axn minus 1 equal to x. Now, what you assert is that this sequence of points form a Cauchy sequence because of the contraction. And the consequence is that, since we have assumed the space is complete, then it has a unique limit point. And that becomes the fixed point of the theorem. Okay, this idea was there in this particular problem or in some other problems also. So all these things have been condensed together and then you got this Gauss fixed point here. But before that, we had this Picard's approximation method. Now let us go to that and then I just quickly tell you what exactly it's all about. So we have assumed f is continuous. That's the only assumption we have made so far, and we have to have more assumptions if you want to get a fixed point. Okay. Right. So you look at this integral equation. Now we define y naught x to be y naught, the constant function y naught. Okay, and then y1 x write as y naught plus integral x naught to x f t y naught d, and so on. You have yn x and so on. This is how you construct the sequence. This is exactly what we did, when I suggested the proof of the contraction method. Okay. And then the point is this: does yn converge? That's a question under the assumptions that we have made. Does it converge to a unique function? And then you see that if it does, what happens is you end up with an equation like this: yn x equal to y naught plus integral x naught to x f what you do is you let n tend to infinity. Then what happens is this converges to some yx. Now you have, nothing happens with n tending to infinity here, so you get y naught itself. Then you have the following thing. Then what happens? See, now there is a question here. Can you jump the integral? Scan the limiting operation, jump the integral, and later jump inside the function. So there are two jumpings that happen. This is equal to integral x naught to x. I have put a question mark. This is to be justified. F t. Eventually, this is it. If all this interchange of limiting operation and the integral and also limiting operation entering the function f, etc. can be justified, then you see that this is essentially yx. So you get a function y which is the solution of the integral equation. And you see that yx naught is, you can show that y dash x equal to f of x yx and y x naught equal to y naught. Therefore, it is a solution of the initial value. That's the problem. Okay. Therefore, now the problem is choosing the right kind of space x. We have not done it for the problem. Now let me do this. The following. Okay. A small effort problem. Okay. So I start with the region I considered. So I have x naught, y naught is the initial data that is given for the problem. So x naught is some point here. What I do is, since this is an interior point of this open connected region, you can enclose it inside a rectangle R with the sides A, this is A and this is B, this side is B and this side is A. So it is actually a the rectangle is x naught minus A cross y naught minus B. This is the rectangle that we are looking at. Okay. Now, on this rectangle, f is bounded. Therefore, I have a m such that mod f is less than or equal to. It's bounded because it's a continuous function, it's a compact set, therefore it's bounded. All sorts of things are used to it. Okay, fine. Now, what do I do? We also need to make one more assumption that f is what do you mean by that? This means the following: f of x y minus f of xz is less than or equal to some k times mod y minus x for all, sorry, y minus z for every x y x z belonging to omega. So we assume f is Lipschitz and or at least for r, you assume it satisfies this condition. So this is what you call the Lipschitz condition. If k happens to be less than, okay, from this one can get the what is called the contraction mapping. So you need an additional condition of this kind to get the contraction. So now what space is to be chosen? Let me do it. Let me look at it. So I choose an h which is equal to minimum of a b by m and 1 upon k, where k is the Lipschitz constant. With this choice, I look at this space C set of all continuous functions, the space of all continuous functions, x0 minus h2 on the interval x0 minus h2, x0 plus h. Now you see that these functions are of course uniformly continuous if you take on the compact. There is no problem at all. So we take this. Now on this we take, so you take an f, this you call x. So f belonging to x. Define norm of f as the supremum of take the sup now, which in turn gives you a metric d of okay. So we get this. Okay. So we consider all continuous functions on the interval x0 minus h to x0 plus h. If you want, you can make it a closed interval and call that x, and on x you put the sup now. Then what happens is x is complete. So it's a complete metric space. Now look at this map. The map that we have defined is A from x to x. What is it? A map is you take a function from here, okay, and then plug it into this one. This is the operation. Ay equal to this means first you calculate this, you get a function of t, integrate it, and then add to y0, that is your ay. Okay? Now, under these conditions, if you can prove that the space that you have, okay, A is a contraction on this space, then straight away from the existence and straight away from the Brouwer's fixed point theorem, you get that there is a unique fixed point, and that fixed point will become the solution of the integral equation, and therefore it is also the unique solution of the initial value problem. Okay. So we need only to verify the following. One is A continuous. Two is A from x to x. That means you have to show that A of y ft yt dt. Let me just estimate this. So I take A yx minus y0. Estimate this. Now this is less than or equal to integral x0 to x dt. now I am keeping x within this part x naught minus h to x naught plus h. Therefore, you can see that this is bounded by this. Therefore, this is less than or equal to m into mod x minus x naught, and that you can show is that this mod x minus x naught. So, what is the condition that you have? Okay, this is this you can show that this is b. Okay, this is less than or equal to. Okay, and therefore you see that for h is the minimum of this, you see that this yx is in this rectangle. The graph of yx lies in this particular rectangle. So that can be easily verified. Now the third thing that you have to prove. So A is a map from x to x. Is it a contraction? That's the next thing to do. You want to prove this is a contraction, you work out the distance between so you estimate this a y minus a z for a y x minus a z x. Okay, so this will give you integral which is less than or equal to okay, this will give you ft Now you see, here you apply your Lipschitz condition. So what does the Lipschitz condition say? The Lipschitz condition says that K is a Lipschitz constant, and you have this one mod yt minus zt. So you take the supremum of that over the interval x naught minus h to x naught plus h. So you can get y minus z into mod, and this is less than or equal to okay. So all that you need is, now you see h you have chosen, you recall that you see h is less than 1 upon k. Therefore this is less than some alpha, or alpha is okay. So it's a contraction. So it's a matter of just verifying A is a contraction. Therefore now we have completely got the problem solved in the abstract function space. There we have seen that A has a unique fixed point, and that fixed point is essentially the solution of the integral equation. It's a unique solution, and you see that it is in turn a solution of the initial value problem. Now this is how you make use of this big theorem to solve this equation. I just thought that I would do it for you, just for change. And how how, this Picard's approximation is very, very old. Okay, it's a very natural thing that mathematicians do. Construct a sequence of functions and hope that everything will fall in place to the limit. The moment the limiting process and then convergence idea was mooted, all these things started springing up. So that's a very old technique, and this is the abstract form of it is contained in the so-called contraction mapping principle. And you can see that you can prove the existence of, and just a remark, you can prove the existence of this. Okay, one remark is that this is a local existence theorem. So you are working on some interval x0 minus h to x0 plus. What is important is that there is a h for which this is true. So this is a solution. Now what one does is you extend it to this side as well as to this side, starting from some other point on the solution, and then you get the solution globally extended. I mean, how far you can go, these are all problems of analysis that you deal with. I think that's the right time to stop that. I think I have slightly exceeded the time, or maybe just exact the time. And thank you very much for this wonderful opportunity. I enjoyed talking to you. Thank you.